Hello dear students, welcome back to channel and welcome back to this playlist in which we are discussing about symmetrical and unsymmetrical faults. So up until now we have seen symmetrical faults, we have seen unsymmetrical faults, we have seen symmetrical components, we have seen positive, negative and zero sequence network, and today most probably we will be concluding this chapter and this playlist with analysis of unsymmetrical faults using busbar impedance and the series faults, right? Because the faults we have seen so far, LG fault, LL fault and LLG faults were shunt faults. So today we are going to discuss about series faults, but before that let's quickly discuss about the unsymmetrical faults which are used by using bus bar impedance matrix and analysis of analysis of my unsymmetrical fault. So let's consider we are having n number of buses. By the way, if you haven't checked out previous videos, the link will be flashing on the top right hand side corner of your screen, so you can click on it and you can check out previous videos, because you will need to understand this, because we have discussed about the bus impedance matrix in previous classes. So if you recall that, that would be very good. If you can't recall that, please check out the video so that you can get better understanding of this class. So with that out of the line, let's move forward. So uh, let's consider we are taking n number of buses in my system, and there is an LG fault occurring at my ith bus. So whenever we draw a connection, it might look like this. See, we are having fault at ith bus, LG fault. So the positive sequence network, we will be replacing it by the Thevenin's equivalent circuit, like the pre-fault voltage. We have given it using this V01 minus I of my bus in the series with the passive positive network, right? So here we have replaced it using positive sequence network. You can see it, and as there is no negative or zero sequence present in pre-fault, so both of these networks will be passive only. So for passive positive sequence network, what will be the value of my the bus voltage? So that value can be given using this formula. V1 minus bus will be equal to Z1 minus bus into I1 minus bus. And what is the formula for Z1 minus bus and I1 minus bus? So earlier we have derived or we have discussed these formulas in detail. So the positive sequence impedance matrix for Z1 bus will look something like this, and the positive sequence bus current injection vector will look something like this, right? So here you are with your formulas. Now according to the sequence network connection, my current I1 minus I raised to F can injected only at the faulted bus, right? Ith bus of my positive sequence network. So what will be the value of this I1 minus bus? So all the networks except for the bus where fault has occurred will be 0, and the bus where fault has occurred will be minus I raised to F 1 minus I. So the positive sequence voltage can be found based on this. So we will be simply using the formula. What is the formula? Formula you can see here: V1 minus I will be equal to minus Z1 minus II into I raised to F 1 minus F. Sorry, 1 minus I. There cannot be 1 minus F. It will be 1 minus I. Alright. So now you have the passive positive sequence network which is present in an impedance Z1 minus II to the positive sequence current I1 minus I raised to F, which are for the negative as well, right? Once we have positive, then we will do the same calculation for negative as well. So again, the equation will remain same. V2 minus bus will be equal to Z2 minus bus into I2 minus bus, same as the previous one. For the bus 1 we will calculate for bus 2 as well. The formula for I2 minus bus will remain same as well, except for the bus in which we are having fault, except for the bus where fault is occurring. All the rest of the buses will be 0, and the bus where fault is occurring, the current will be minus I raised to F2 minus I. And same thing will happen for voltages as well. So V2 minus I will be equal to minus Z2 minus I into I, I raised to F2 minus F. So you will be calculating the negative sequence voltages as well. And once you find the negative sequence voltages, uh, you can go for the zero sequence network as well. And again, I don't have to mention that same thing will happen. V0 bus, the formula will be same as the previous two buses. For V0 bus, same formula will be executed for I0 bus and V0 minus I as well. So I'm not going into detail, I'm not going to mention the formulas again. Now that you have all three sequences, and you have already derived the zero sequence network, which has offers an impedance Z0 minus II in the zero sequence current. We remember earlier we saw that whenever we have a balanced system, the positive sequence, negative sequence, and zero sequence current will be equal. So the current will be equal. So here you can see the fault current for I1 minus I, I2 minus I, and I0 minus I are equal. And what will be the value? So that is also we have derived in earlier class. So the value will be V1 minus 1 minus I raised to 0 divided by the sum of all three impedances, positive, negative, and zero sequence impedances, plus 3 times the fault impedance. And that will be the formula for your positive, negative, and zero sequence fault current. Now similarly, we can also compute the current for LL fault and LLG fault as well. So I'm not mentioning it in this calculation. Now once we have the current values, what do we have to do? We can calculate for the post fault voltages for any bus. So for passive position sequence network, the voltage developed at bus K due to injection of the ith bus, what will be the value? So again, the formula will remain almost equal. V1 minus K raised to F, so the fault voltage will be equal to V01 minus K minus Z1 minus IK into I raised to F1 minus I. Now here the value of K will remain, will keep changing from 1 to up to number of buses to n. And v raised to 0 1 minus K is the pre-fault positive sequence voltages, of course at bus K. And similarly Z1 minus K is the ikth component of my one bus, Z1 bus. And where did this formula came from? So this formula came from this. This is the general formula: V1 minus K raised to F is equals to Z1 minus IK into IF1 minus I. Right. So you are basically taking the multiplication of fault current and your impedance matrix, bus impedance matrix, and you are finding the voltages. And as the pre-fault negative sequence bus voltage is 0, the post-fault negative sequence bus voltage can also be found using the same formulas. So I have not mentioned the formula again here. You just have to replace 2 instead of 1 here in the values of current and impedance. Same will be the true for voltage. and you will be able to find the negative sequence or negative sequence and zeroth sequence voltages. And once you calculate zeroth sequence, negative sequence, and positive sequence voltages, so you will have all the post fault sequence voltages and sequence currents in the line. No, you will not have sequence current in the line. You will be finding the sequence current in the line, right? So you can find the sequence current in the line based on the admittance. Remember what is the admittance? Admittance is basically the inverse of my impedance. So you can find the value of y1, y2, y3, sorry, y1, y2, y0, and you can calculate the current, and the formula for the sequence current is given here. So I1 minus Pg will be equal to Y1 minus Pg, and into subtraction of your fault current, right? Sorry, subtraction of the fault voltages, and by doing that you can find the value of I1 minus Pg, I2 minus Pg, and I0 minus Pg. And once you computed this sequence currents, you can find the phase voltage and current easily from this formula. Vp is equals to a into Vs Ip is equals to a Is. Remember what was the a? The alpha matrix having so many number of alphas and ones, so that was the a. And you know Vs and Ip as well. There is a printing mistake. Vs will not be small, V will be capital, S will be small, and you will be finding IP as well. So this method will require computation of bus impedance matrices of all three sequence networks, and because you have to do all these maths, the whole process will get very much tedious and time consuming, because basically to find the or to calculate the sequence networks for all three buses is it is very tedious, right? You need to invest so much time and brain, right? So for all three sequence networks it gets difficult, but once the impedance matrices have been formed, then uh, you can carry out your fault analysis very easily for all the buses, right? And that is also the aim of this fault analysis. That is why we are using this unsymmetrical fault analysis with bus impedance matrix, so that you can generalize it, you can use for all the buses, even for any changes in the power network, right? Because remember we saw earlier how we can modify our bus impedance matrices. We saw four different cases in which we were adding a new bus in the pre-existing bus or reference bus. We saw the four cases, so based on that the improvements can be also made, and you can make the improvements in your calculation as well very easily. Now let's see the computer calculation of my fault current, or basically what will happen in when we do that. So the current and voltages that activate the relay are the current and voltages which flow or appear immediately after the fault occurrence. And we all know the fault current is normally very high, and who interrupts that? So it has been it's interrupted by my circuit breaker. So both fault current and voltages are needed to be calculated, and the voltages and current during these faults are used to set the relays. So the quicker you calculate the voltages and currents, the better it is for us, right? So you have to calculate it as fast as possible. So the initial fault current is used to determine the required momentary duty of my breaker, and the uh, current and the voltage a short while later on are used to calculate the required interrupting capacity of my breaker as well. So it is very important to find this current and voltages, because it is helping us so many ways. It also helps us to find the short circuit capacity of my circuit breaker. So we have to find the voltages and currents, and this calculation tells us how we can do it based on the flow chart. So the basic aim of this fault study is to determine the impedance matrix of my system. So the end goal is to determine the impedance matrix, and the impedance matrix elements along with conditions of fault are used to calculate the fault current and pre-fault voltages, right? So what do we do? Initially we read the values. We read the total number of buses we have, and based on that uh, we form the zero sequence matrix. Z bus 0 we called it, and then we also form positive and negative sequence matrices, Z bus 1 and Z bus 2, for whatever number of buses I have. Let's say I'm having a n number of buses. Once we form all three matrices, what we will do, we will see how many lines I am having, right? How many lines I'm having in my bus. So after determining number of lines in the bus, what we can do, we can say, like, from bus number, let's say ni, to bus number nij, we can calculate the zero sequence line impedance, and then we can calculate the positive and negative sequence line impedances as well, right, for each and every line. First we do for the buses, positive, negative and zero sequence component, uh, positive, negative and zero sequence impedance, and then for lines in each bus, positive, negative and zero sequence impedance. Once we find out the impedance for each line in each bus, then we will determine what type of fault has been occurred. So what we will do, we will check if this is a solid single phase to ground fault. If our calculation suggests that yes, it is a solid single phase to ground fault, then we will compute the fault current. We will calculate the post fault bus voltages, and then we will calculate the line current, right, after the fault for solid single phase to ground fault has been occurred. If that is not the case, then we will check for other faults. After that, we will check if the fault is a line to line fault. If it is a line to line fault, then again we will compute the fault current. Then again we will determine the post fault bus voltages and the line current after fault for line to line fault. If that is not the case, then again we will check which one remains. The remaining one is the if it is a solid three phase to ground fault. If that is the case, then again we will calculate the fault current, post fault bus voltages, and again line current after fault for solid three phase to ground fault has been occurred. If even that is not the case, then in the last one we will check if it is a solid double line ground fault, and if that is the case, we will repeat the same procedure as well. We will calculate the fault current, positive bus voltages, and line current after the fault for solid double line to ground fault. And once we calculate it, like, the fault can either be these four of them, right? If that is not that is not the fault, then which other fault can occur? The series faults, right? So series fault, we will not be going through all the impedance matrix thing. We will do something else. What we will do, we will see that, but for now know that this will be the formula. And once we determine the current voltages, then we can stop the loop. So that's how you do the calculation for fault current using computer algorithm. Now let's see the series type unsymmetrical faults. Remember, I told you there can be two type of series type unsymmetrical faults. Mostly all the series type unsymmetrical faults are open conductor faults, in which in what happens in such cases, your conductor tears apart, or it gets opened. right? Your line gets opened, so it is very vulnerable. So it causes such a situation. So two types of fault can occur uh, in series in line. First one is the one conductor open. So basically here you can see I'm having three phases, A, B and C. uh, One conductor of A phase has been opened here. So when such thing happens, the remaining conductors are as it is in B and C phases. So when such thing happen, basically conductor is open, so there will be no flow of my no flow of current in my A phase line, right? And as there is no flow of current in my A phase line, what will happen? The voltages of phase B line and phase C line will become zero. Now we already know that the symmetrical components, sum of symmetrical components is zero, because uh, it is not my line is not getting unbalanced. So sum of all three symmetrical components will be zero, and the sum of not sum of but all three voltages of all three phases will be equal. And what will be what will be the value of it? So value will be 1 by 3 va12, or va23, or va13. You can call it whatever you want, because all three are equal. So when this voltages I've just mentioned about are positive, negative and zero sequence voltages of my phase A, so what we can do, we can form an equation of sequence current and sequence voltage of my phase, and based on that we can form one conductor open equivalent sequence network. And it will look something like this. We are having positive sequence, negative sequence and zero sequence current. ia1 is going and ia2 and ia3, ia0, the current coming out meeting here, which means equivalent is 0. va1, va2, va0, all three going in. So what does it indicates? It indicates that open conductor condition leads to an equal series voltage drop in all three sequence networks in the direction of current flow. Pretty much simple. The next one is the two conductor open fault. So what two conductor open fault does? So in this case what will happen? Two conductors will tear apart and will be open. So here you can see phase B and phase C, the conductors of phase B and phase C have been opened. Phase A is remaining as it is. So obviously the current will not flow through the phase B and phase C, and voltage across phase A will become 0. And in such condition what will happen? The voltage sum of all three phases will become 0, and the current will become equal in all three phases. Not phases, I'm talking about symmetric components, positive, negative and zeroth. So the positive, negative, zeroth sequence voltages sum will become 0 for whatever line the current is flowing through, and the sum of positive and negative and zeroth current will be 1/3 into ia, because basically all three of them are in phase. And based on that equation, the uh, the diagram we will get will look something like this. And in that you can see that ia, i2, i1, ia1, ia2 and ia3. ia1 going from ia1 is going here and connecting at va0. ia2 is moving from here and connecting at va2, and ia0 moving from ia0 and connecting to va2. So it indicates that sequence network for this fault are connected in series, right? So that's the wrap for sixth chapter. I might come up with um, some other videos related to power system, but I'm not sure what I will come up with. So please keep if you have any suggestions, please mention them in the comment section. If you have any feedbacks or any queries related to this class, you can mention them in the comment below as well. I will be taking leave. Thank you very much for listening and have a great day. Thank you.